All right, clip number 3 for section 1 notes. These are going to be the 3 applied examples for lines and segments that intersect with circles. And this first example, actually these first 2 examples, we're going to be referring to a previous chapter on right triangles. And I'm going to talk about that reference in just a second. But we're given this diagram. Surprise, surprise, there's a circle. And then they show us this triangle. A couple things to point out just to be aware of here. This is circle P, so this is a specific notation. Circle P, you'll see a little circle with a dot in the middle. That's just the geometric symbol for a circle. You always name a circle based on the center point. So when I say circle P, that means literally in this diagram, P is the center of the circle, right? And that matters in this case because if P is the center and T is some point on the circle itself, that forces PT to be what we call a radius. So that 12-unit measurement right there ends up being a critical piece of measurement for this circle. We could actually solve for all the measurable, quantifiable facts about the circle just based on that number. Okay, but that's not quite what the question is based around. It was just kind of worth pointing out that. The other thing I want to point out here, you're going to see it specifically the difference between this problem and the next problem with how they can draw these diagrams. But I want to point out that from S all the way to the center of the circle is 37 units, and it doesn't ask you about it here in this problem, but this radius from point P to this edge right here is still 12 units because it's the same radius. So if it asked you the distance from this point right here out to S, you would just subtract 12 from that 37. Okay, little things like that will pop up in your examples in your problems. So just being aware about how to solve that and think about it abstractly can come in handy. All right, but let's get back to what the question is asking. We're shown this diagram. They show us this triangle that's basically interacting with this circle, where one of the corners of the triangle is the center of the circle. Okay, and they ask us, is segment ST tangent to circle P? ST being this leg of the triangle. And based on the information they're giving us, it doesn't seem like they're actually telling us anything about whether or not it's tangent. Based on those numbers, just on the numbers themselves, it doesn't tell us whether or not, if I were to expand ST off into forever and make it a line, whether or not T is the only place it will ever touch the circle. Even at a microscopic level, it's possible that it does pass a little bit through the circle and intersects twice, thus making it a secant and not tangent. So there's something about these numbers that I need to figure out whether or not ST is tangent. And here's the massive hint that I'm going to suggest you write a note in your margin. This refers back to that first theorem that we talked about. If a line or a segment is tangent to a circle, it has to form a perpendicular or 90-degree angle with the radius that connects to that intersection point. In other words, if this is tangent, if ST is tangent, then angle STP, angle T up in here, needs to be 90 degrees. It has to be. That is the only way for that to be tangent. If it's anything other than 90 degrees, it's just simply not tangent. Okay, so if that's 90 degrees, here's where you have to connect the dots to a previous chapter. If that's 90 degrees, that forces this triangle, triangle STP, to be a right triangle. And if it's a right triangle, then I can use the Pythagorean theorem. Okay? So I can actually use these side lengths. I can use these side lengths to determine whether or not this is a right triangle. Basically, if this is 90 degrees, that forces this SP segment to be my hypotenuse. All right? Meaning 35 squared plus 12 squared would have to equal 37 squared. That's the Pythagorean theorem right there. All right? So it is possible. It's asking me if it is tangent. So it's actually possible that it's not. If it's not tangent, then a squared plus b squared will not equal c squared. And that's ultimately what we're going to test. The math itself is actually pretty straightforward and basic. We're just doing squareds, okay? But we're going to test whether or not something is true. So let me jump to the whiteboard. And I'm going to simplify this drawing a little bit. Let me just draw the triangle. So we're testing to see if this is a right triangle. So really, this part right here is a question mark. Is it 90 degrees? And then the side lengths that we were given are the following. We're told that this leg here is 35 units. This one here was 12. This one happened to be the radius of that circle. And then this whole hypotenuse was 37, which for the record checks out because the hypotenuse should be the longest of the three. So that's how you can also tell if it's the hypotenuse or not. But essentially, if I'm testing whether or not this is 90 degrees, I need to test the Pythagorean theorem. So I'm going to ask myself, does 35 squared plus 12 squared, the two legs that form the right angle, equal the hypotenuse squared? And that's a question mark. These are real numbers I'll be able to solve for. If it equals whatever this says on this side, it's a right angle. The Pythagorean theorem would be true. If they don't equal each other, it's simply not a right triangle, and therefore it can't be tangent. Well, don't be a hero. Do this stuff on your calculator. 35 squared, or 35 times 35, comes out to 1225. I happen to know 12 squared off the top of my head is 144. And 37 squared, or 37 times 37, gives me 1369. One last little piece of addition to do. If you were to add 1225 and 144, you would actually find that to be 1369. They do, in fact, equal each other. That doesn't seem particularly significant. But what does this mean? Yes, they do equal each other. That means that this must be a right triangle. Because the Pythagorean theorem only works if it is a right triangle. Had it been any other number equaling 1369, it simply would just not be a right triangle. It's obviously a triangle. It just wouldn't be a right triangle. So back to the question, to answer that directly, is segment ST tangent to circle P? Yes. Because again, it broke down to this simple result. We just proved that this angle right here had to be 90 degrees based on those measurements. And because that's 90 degrees, that forces ST to be tangent to the circle at point T. So we used Pythagorean theorem to prove that ST was tangent. All right. Let me erase the whiteboard. We'll move on to example number 2. Example number 2 will also be a little tricky. We're going to use actually the same exact strategy of using the Pythagorean theorem, but it's going to be presented a little bit differently. All right, again, you're given a diagram with a circle. Again, we see a triangle involved with that circle. In this diagram, we are told that point B down here is a point of tangency. What does that mean specifically? If point B is a point of tangency, that means that AB, this segment right here, is a tangent segment. Meaning that if I were to continue AB off into forever in both directions, making it a line, this is the only spot it would ever touch the circle. Okay? So what does that imply? The fact that this is a point of tangency and that this is tangent to circle C, that forces angle B right here to be 90 degrees. That's that first theorem again. And because angle B here is 90 degrees, that forces this whole triangle ABC, to be a right triangle, meaning I can apply everything, all the baggage that's tied to a right triangle, namely Pythagorean theorem, to this result. But here's where it gets a little funky. So in this diagram, all I'm told is that basically AB is a tangent segment. My job here is to solve for the radius of the circle. They've told me that AB, this tangent segment, is 80 feet long. And here's where I wanted you to notice the difference between this diagram and the one before. In this one, we were told that the distance from this outer point to the center, as shown by these little lines right here, the whole distance was 37. Notice the difference with this diagram. It does not tell me everything from A to C, the center, is 50 feet. It only tells me that's 50 feet from A to the circle. The rest of that distance is that unknown distance R, the radius, which is the same distance as this leg of the triangle. We're going to use Pythagorean theorem here, and so I want you to pay attention because we're going to actually be referring to a chapter from first semester, and this can get a little tricky. So let me jump to the whiteboard again. Draw this triangle to start with again, one more time. In this case, unlike in the last problem, we know for a fact that this is a right angle because we were told it's a point of tangency. Great. We were then told that this was 80 feet down here. And here's where it got a little bit different. Just to kind of use those colors. We have some unknown radius. And then the distance from that outer point to that circle was 50 feet. Now, since this is a right triangle, the Pythagorean theorem has to be applied here, meaning this leg squared plus that leg squared has to equal the hypotenuse squared. But the difference here is that these two things together make the hypotenuse. In other words, this hypotenuse is not 50 feet long. It's not r long. It's 50 and r long. And we represent that with addition. So pay attention to this, because this is where, again, it's going to get funky. 80 squared plus r squared, that's the leg squared plus the leg squared, a squared plus b squared, is going to equal, here's where it's weird, all of the hypotenuse squared. But the hypotenuse is 50 plus r. It's weird, I know. All right, this, for the record, is something we did in first semester. This is polynomial multiplication. I can actually rewrite this as 50 plus r times 50 plus r. That's what the squared fundamentally does. All right, well, first off, over here on the left, this is something that can be done on a calculator, so nothing really overwhelming here. That's 6,400, 80 times 80, plus r squared. That stays r squared because it's a variable. But 50 plus r times 50 plus r, just to write it out, is going to be 50 plus r times 50 plus r. I write it this way so that we can see the distribution method that we learned in first semester with polynomial multiplication. So in this case, I'm going to take that first object, the 50, and multiply it throughout that parentheses. And I'm going to take that r and multiply it through the parentheses. So let me write that out really quickly. 50 times 50 gives me 2,500. 50 times r gives me 50r. Done with the first object. Move on to the second. R times 50 also gives me 50r. And then r times r gives me r squared. So I get this long, gross polynomial on the right-hand side. Don't worry, it's going to clean up really quickly. On the left-hand side, I still have 6,400 plus r squared. And this is actually no different than something you saw in first semester with polynomial addition. Combine like terms. Let's look at those r squareds. If I want to combine them together, subtract this r squared from the right-hand side, we're actually going to get the r squareds to cancel. So once I do that, I just get 6,400 on the left-hand side. R squareds cancel. On the right-hand side, I still have 2,500. I'll be able to combine those. Let me go ahead and combine these r's. 50r plus 50r gives me 100r. And now I can just go about solving this like anything else. Subtract 2,500 from both sides. It comes out to 3,900 is equal to 100r. Divide both sides by 100. R is 39 feet. So the real trick here was this up here at the top. Understanding that that hypotenuse, all of that for the Pythagorean theorem, that hypotenuse squared is the 50 plus r. That made things a little complicated as far as polynomial multiplication goes, but it's nothing we haven't done before. It looks scary, but again, it's nothing we haven't done before. This one is trickier and intimidating, so if you need help on problems like this, feel free to ask. But I'll go ahead and erase this now and move on to our last example, which will be a lot faster than these last two. All right. So both that problem and the one previous to that dealt with that first theorem that tells me that anything that is tangent to a circle is going to make a 90-degree angle, going to be perpendicular at that point. This one is going to be using the second theorem. It's actually pretty obvious with how the diagram's actually drawn. I have a circle, and then I have this exterior point with those two tangents. And I'm just going to briefly talk through this because I've only got a few seconds left on my recording time. So let me just identify this, what's happening here. We're told that RS is tangent. We're told that RT is tangent. It's that common external point. The second theorem tells me anytime I see this, these two segments need to be congruent to each other. They need to have the same measurement. So fundamentally, geometrically, I'm left with this, that RS has to be congruent to RT because of that second theorem. And then because of that, I can set up the following equation. 28 has to equal 3x plus 4, and I can